This video is going to be a sequel to the previous video in which we looked at near resonance and beats. So, in this video we're going to look at actual resonance. Now, again, the context is we have second order linear constant coefficient, but we've specialized to undamped. We have no damping here. And so here we go. And so the homogeneous solution, sort of what this oscillator would do on its own, is just pure oscillations, cosine and sine, with a 3 right here, right? If you have a 9 here, we end up with the square root. We end up with a 3 right here. Okay. But now we have a sinusoidal forcing term over here. And in the last video, we had exactly this situation, and we had omega at 4, and then we looked at 3.5, we looked at 3.2, 3.1, and also on the other side 2.8, 2.9, and we saw some interesting behavior as this omega approached the 3 that is in the homogeneous solution. So where the forcing frequency was getting close to matching the natural frequency, right? And like I said, we saw an increase of amplitude. Things were getting closer and closer to being in sync, but we also saw beats because after a while it would fall out of sync and then it would come back down again. So we would see this superposition of a quicker oscillation, but with a slower, bigger oscillation on top of that. So it would get bigger and then smaller and then bigger and then smaller, all the while oscillating pretty quickly, like amongst those bigger oscillations. And those were the beats that we have mentioned. Okay, but our formula failed right when omega got to 3 because we actually ended up dividing by 0 at one point in our solution formula. So now we're back to the drawing board and we're going to try to come up with a solution when omega is 3. So I'm going to go in here and I'm going to put a 3 here. So we're actually dealing with what we're going to call the actual exactly resonance case. Okay. Now the homogeneous solution is still the same, right? Because that has nothing to do with the forcing. That's when you put a 0 here anyway. But now let's try to get the particular solution. All right. So we complexify, as we've been doing with all our sinusoidal forcing problems. So we get an e to the 3it, right? That's the complex version of cosine 3t. Cosine 3t is the real part, so when we solve this guy, we're going to take the real part of our solution, and that should be the answer to the one we really want. All right, so now, normally what we would do at this point is we would guess d e to the 3it. However, here's the problem, and I'm going to stop us before we go further and really see the problem hit us right in the face. We won't be able to get this to work, because the homogeneous solution here to the complexified version, which usually we don't worry about because we already got the homogeneous to the original, but the homogeneous solution to the complexified version, if I just really quickly write that down, right, that would be e to the 3it. That would be a solution to that. This guy works in the homogeneous. And so our forcing is the same as a solution to the homogeneous. And so we've seen this before, and we saw that we can't do our normal guess. But we also figured out a workaround. We figured out that the workaround is to throw in an extra multiple of t. And that exactly in this case, when it is otherwise failing, this will work. All right, so let's see what we get. So this is going to be our guess, and of course what we have to do is figure out the d, the undetermined coefficient, and get that right. So let's work that out. I get a first derivative. Now, of course, I have to use the product rule because we have t times an exponential, and I think that's what we get. And then when we go to the second derivative, all right, I'll keep the video going for this part. So we would have the first, the 3i dt, I'll kind of group the 3i d and t together and call that the first, and the exponential will be the second. So the first times the derivative of the second. The derivative of the second is, of course, itself, but then another 3i is going to pop out. So I think we'll get it, because of the I squared, we'll get a negative 9 dt e to the 3it. plus, and then it'll be the derivative of the first part times the second part. But the derivative of the first part is just 3id times the second. And then here we have we don't need a product rule for this term, just a 3i pops out, so 3id e to the 3it. Right, so actually these two guys combine for a 6id e to the 3it. All right, so that's the second derivative. Now I'm going to plug it into my complexified differential equation. So I get 6id e to the 3it plus 9 times y, so 9 dt e to the 3it. And this is supposed to equal, well, 1 e to the 3it. Okay, so the e to the 3it's cancel, and what do we have? We have 9 plus, or excuse me, I'm sorry, I did not put everything in right. I forgot the minus 9 dt e to the 3it. I was panicked for a second and thought things were not working out. All right, those two terms together are the second derivative, and that should have gone in there. Okay, my apologies. Now, yeah, this is much better, right? So the t e to the 3it terms, we have a negative 9d and a positive 9d. Those cancel. That's what's supposed to happen. And so we have 6id has to equal 1. All right, so d is 1 over 6i. Now I can put this sort of in standard form. I can multiply by I and I. So I get negative I over 6. Okay. So my guess, which is right here, I now know the undetermined coefficient d. So it's negative 1/6 I t e to the 3it. And combining that with my homogeneous, which was cosine and sine of 3t. Oh, excuse me. Wow, I'm making mistakes all over the place. This is the complexified solution, right? So we need the, remember it was cosine, so we need to take the real part of this. So let's write this out. So we've got negative 1/6 I t, and then our complex exponential. It is time now to break that down into cosines and sines. And again, we want the real part. Now, we're multiplying by an I on the outside, so when we multiply this onto the cosine, that part will actually be imaginary. But when I multiply it onto the other part, there's going to be the real part, because an I times an I will be a negative 1. So what do I get? I get 1/6 t sine 3t. That's my real part. Now, I don't really need it, but let me just finish up the rest of this. It would be minus 1/6 I t cosine 3t. That's the imaginary part. But yeah, there's the real part. So my yp for my original problem is 1/6 t sine 3t. All right. Now I'm ready to combine it with the homogeneous. So I've got this, and then I have a cosine 3t plus b sine 3t. All right, so this is what the formula should look like at resonance, when the forcing frequency is matching the natural frequency. And again, so that I can graph this, let me go ahead and put in just a 1/4 for A and B. Let's assume the initial conditions are such that that's how A and B came out. And all right, let's try this out. Okay, so here was our old near resonance. You can see this was the old one, the old solution with omega at 3.2. Here it was at 3.1, right? We saw this amplitude getting bigger and bigger, but of course it failed at 3. Let me leave that there. Now I'm going to turn that one off, or actually let me leave it on, but I'll turn it off in a second. And here's the formula we just found with the 1/6 t sine 3t. So let me Boom, put that in. Now, okay, let me take away the first one so you can see this better. Wow, okay, so you see the oscillations, and they are just getting bigger and bigger and bigger. Now, is this just a really big beat that's eventually going to come back down and we're just not zoomed out enough to see it? Well, let me zoom out a bit. Let me go to 10. Doesn't look like it. I'll go out a little further to the right. Let's do 150. So okay, let me go out. Let me go up again. Nope. All right, I'm really zoomed out now, and you see that this is not coming back down. In fact, the amplitude is growing linearly. Wow, so this is actual resonance. The thing starts vibrating more, 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 and it's just never going to stop. In the real world, of course, whatever is doing the oscillating will eventually break somewhere at this point. It will break. The glass will shatter, right? That's the idea. So there you go. That's what the resonance solution looks like, and you've seen now how to get it. And again, it's interesting. Every time we've run into a problem with these linear differential equations, the problem is always solved by throwing in a t, right? That's always been our go-to solution, our workaround, and it worked here. Okay, so resonance is an important thing. Now, again, resonance has to be just right. It has to be where the sinusoidal forcing frequency is perfectly matching what the oscillator wants to do on its own anyway. And then you get this behavior. Okay.